Welcome to GERO Mathematics and Statistics lessons, and Merry Christmas to all of you out there. Thank you for your subscription to our channel. Thank you for your likes and comments to our videos. Thank you for your shares of our videos. We are very grateful from the decks of GERO. If you haven't subscribed to the channel yet, please do that now by clicking the subscription button below and endeavor to turn on your notification bell. Thank you very much. In our first lesson on probability, we answered the question, what is the probability of an event from an empirical perspective, and we gave some general definitions to probability of an event. In this lesson, we shall consider answering this question, what is the probability of an event from a set theoretic perspective. So we shall be giving a set theoretic definition to the probability of an event. For us to give a set theoretic definition to the probability of an event, we must start with discussing the sample space. So every random experiment has a sample space, and we shall begin this lesson with discussing what a sample space is. Okay, so remember from our previous video that a random experiment was described to be an experiment whose outcome cannot be predicted in advance. So any experiment whose outcomes cannot be predicted in advance is a random experiment. What then is the sample space for any random experiment? So let's begin. The sample space for a random experiment, is the set of all the possible outcomes. Is the set of all the possible outcomes for the random experiment. Okay? So what we describe to be the sample space of a random experiment, or for a random experiment, is the set of all the possible outcomes for that experiment. Now take note, outcome in this case means the result of that experiment. Okay, so by outcome we are referring to the result of the experiment, the random experiment. And by random experiment we are referring to an experiment whose outcomes or whose results cannot be predicted in advance. So what we call the sample space for a random experiment is the set containing all the possible outcomes for the random experiment. Now, how do we represent or denote sample spaces? A sample space for a random experiment, is conventionally denoted by S. So uppercase S represents the sample space of a random experiment conventionally. Okay, so wherever you find S in probability, uppercase S, it means you are talking about the sample space of any given random experiment. Okay, now I'm going to show you in this video how to form sample spaces for different random experiments. Remember, in our previous lesson we talked about 4 different types of random experiments: the tossing of a fair coin, the tossing of a fair die, the shuffling of a card deck, and of course the aiming of any given target. So let us start with the case of a fair coin. So I'm going to show you here how to form sample spaces for different random experiments, especially that which concerns the fair coin and that which concerns tossing a fair die. So let's consider tossing a fair coin, one fair coin. So tossing one fair coin. Now, whenever you carry out a random experiment such as this, tossing a fair coin, there must be a corresponding sample space. And the sample space for tossing a fair coin should contain the set of all possible outcomes for that particular experiment. So when a fair coin is tossed once, what will be the sample space? Now take note, let me put beside here a fair coin. Now remember that our description of a fair coin in the first video told us something about a fair coin. Okay, what did we say? We said that a fair coin is a coin that has no possibility of landing erect, but only has the 2 possibilities of landing on either side, okay, of its base. So this is a fair coin. Let's call this the head, being the surface of interest. Automatically this becomes, the bottom becomes the tail, or the other side becomes the tail. Okay, so now what will happen when you toss one fair coin once? It will generate a sample space S that contains just head or tail as two possibilities that you could have. Okay, so when you toss one fair coin once, it has a sample space containing just two possible outcomes. It is either you have a head or you have a tail. That is when you toss one fair coin. So tossing one fair coin gives a sample space S equals the set of head or tail. Now, what about tossing two fair coins? What about tossing two fair coins? Okay, so let's see what will be the sample space for tossing two fair coins. So if you toss two fair coins, this and this. If you toss two fair coins, this and this is coin 1 and coin 2. Okay, so when you toss two fair coins, there are four possibilities that could emerge. Number one, the first possibility is that you could have the first coin showing you a head. Okay, let's use the shaded portion as a head. So you would have the fair coin showing you a head, the first fair coin showing you a head, and the second fair coin shows you a tail. So let's use a white side to represent the tail. Okay, now that is possibility number one. So this is possibility one. Now possibility two is that the two coins could land after tossing both of them at once, and the first could give you a head and the second could also land showing you a head. So that becomes possibility number two. It is also possible that in tossing the two fair coins once, both of them could land showing you tails, and that becomes possibility number three. Okay, then finally, it is also possible that the first coin could land showing you a tail, but the second coin would land showing you a head, and that becomes possibility number four. So when two fair coins are tossed once, there are four possibilities. What are those four possibilities? Both of them could land showing you head and tail, the first being head, the second tail. Both of them could land with with both of them showing you heads. Both of them could land with both of them showing you tail. Both of them could land with the first showing you tail and the second showing you head. So those are the four possibilities. And if you want to write S, the sample space, it becomes a set containing head tail as a possibility, head as another possibility, tail as a third possibility, and tail head as a fourth possibility. Making it four possibilities for the tossing of two fair coins once. Okay, so what are we doing? We are trying to show you that a sample space for a random experiment is the set of all possible outcomes for that random experiment. And for the tossing of a fair coin, which is a random experiment, you can only have two possibilities, being head and tail, or head or tail. So when you toss one coin once, the coin could land showing you a head, or it shows you a tail, and that would be the two possibilities you could actually have for that experiment. If you toss two fair coins once, the first coin could land showing you a head when the second one shows you a tail. The two of them could land showing you both of them heads. The two of them could land showing you tails, and the two of them could land with the first showing you tail and the second showing you head. So giving you four possibilities. Now, aside these four possibilities, there are no other possibilities that could occur in the sample space. So the sample space is an exhaustive list of all the possible outcomes for a random experiment. Now, let us proceed to taking a case of three fair coins tossed once. Okay, so when three fair coins are tossed once, so let's consider tossing three fair coins. So when you toss three fair coins once, that is coin number one, coin number two, coin number three. So this is coin one, coin two, and this is coin three. Now, when you toss three fair coins once, let's say the shaded portion are the head. The shaded portions are the head. Now, when you toss 3 fair coins once, there is the first possibility that the 3 of them could land, showing you head, head, and head. It is also possible that the 3 of them could land with the first 2 showing you heads and the last one showing you tail. It is also possible that the 3 of them could land again and you end up having head, tail, tail. The first showing you head and the other 2 showing you tails. It is possible also that the 3 of them could show you tails. So those are 4 possibilities so far. Are there more possibilities when 3 coins are tossed once? Yes, there are. So this is not an exhaustive list. Let us continue. It is possible that the first could show you tail, the second could show you tail, and the last would show you a head. It is also possible that the first could show you a tail, but the other 2 would show you heads. It is possible that the first could show you a tail, the second could be a head, and the third would be a tail. Or the first could be a head, the second could be a tail, and the last could be a head. So that gives us 8 possibilities in total for 3 fair coins when tossed once. Remember, the tossing of a fair coin is a random experiment, and we are looking at developing sample spaces for random experiments. Developing the sample space for a random experiment simply requires you to give an exhaustive list of all the possible outcomes. So in this particular experiment of tossing 3 fair coins once, the random experiment will generate a sample space containing 8 possible outcomes, meaning that S can be written as head, head, head as one possible outcome, head, tail, tail as another, tail, tail, head, tail, head, tail, head, head, tail, 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 head, head, and finally head, tail, head as 8 possible outcomes for this given random experiment. So now you could go on and on to develop sample spaces for the tossing of 4 fair coins. It is possible to do that. Let's consider doing that. Okay, so if we want the sample space for tossing 4 fair coins, okay, that will be tossing 4 fair coins. Okay, so the sample space S for tossing 4 fair coins will be generated as follows. Now take note of one thing. S in this case will contain the following. It is possible that the 4 fair coins will be thrown and they land, showing you all of them heads. It is possible that the first 3 could show you heads and the last will show you a tail. It is possible that the first 2 will show you heads, the other 2 will show you tails. It is possible that the first will show you head and the remaining 3 will show you tails. It is possible that the first will show you a head, the second will be a tail, the third will be a head, and the fourth will be a tail. It is possible that the reverse could be the order of the day. That is, head could be, tail could be first, head second, tail third, and head fourth. It is possible to have tail with 2 heads in between and then a tail. It is possible to have a head and in between you have 2 tails and then a head. Now if you count the number of possibilities, you have 1, 2, 3, 4, 5, 6, 7, 8. So these are 8 possibilities, but the question is this the sample space for the tossing of 4 fair coins? No. Why is it not the sample space? Because it is simply because this is not an exhaustive list of all the possible outcomes. So there are more outcomes than these ones we've mentioned. So let's continue. Now it is possible to start with having 4 tails, followed by having 3 tails showing first and then a head. You could have 2 tails showing first and then 2 heads following. You could have a tail and 3 heads following. Okay, now how many do we have so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now are those all the possible outcomes? No. You could have a head, a tail, and a head. You could have a head, a tail, a head, and a head. You could also have a tail. You could have a head, a tail, and a tail. And finally, you could have a tail, a head, and a tail. And this will give you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 possible outcomes for this random experiment. Now, if you check very well, among the 16 outcomes, you would notice that none of these outcomes are repeating themselves. The pattern is not repeated for any outcome. So head, 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 tail, head, head, tail, tail, head, tail, 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 head, tail, head, tail, tail, head, tail, head, tail, head, head, tail, head, tail, tail, head, tail, 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 head, tail, tail, head, head, tail, head, 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 tail, head, head, tail, head, head, tail, head, head, and tail, tail, and then finally tail, tail, head, tail. So these are 16 possible outcomes. Now, we could go on and on, but one thing you must observe is the fact that even before carrying out the random experiment of tossing one fair coin once, two fair coins once, three fair coins once, and even four fair coins once, even before carrying out these activities or these experiments, you could actually predict or tell the exact number of outcomes to expect even before carrying them out. How do you do that? We could use the generalization here that the cardinality of the sample space for tossing a number of fair coin will give you 2 raised to power n or 2 raised to power x, where x in this case stands for the number of coins. Okay? So x stands for the number of coins, ns denotes the cardinality of the sample space, and by cardinality we are referring to the number of outcomes you have in the sample space. So let's see. Now, if x is 1, we are going to have 2 raised to power 1. So when x is 1, ns will be 2 raised to power 1, giving us 2. And of course, if you remember, the number of outcomes we had in the sample space for tossing one fair coin was 2, head and tail. Now, when x is 2, we have ns equals 2 raised to power 2, giving us 4 possible outcomes. When x is 3, of course, x in this case refers to the number of coins. ns will give us 2 raised to power 3 possible outcome, which is 8. 2 raised to power 3 possible outcomes. Now, when x is 4, ns will give us, when x is 4, ns will give us 2 raised to power 4 possible outcomes, which in this case would be 16. So you can actually see that even before carrying out a random experiment of tossing a number of fair coins, you can actually tell what number of outcomes will be, what the possible number of outcomes will be in the sample space. Now, from this we can deduce that when x is 5, ns will give us 2 raised to power 5 possible outcome, and that will be 32 in the sample space. 32 possible outcomes in the sample space. I'm going to leave that to you to try, okay? So you try that in your own time, okay? Now, let us go to the next type of sample space I would want us to look at. What if we want to look at the sample space for tossing one fair die? So, let's consider the sample space for tossing one fair die. Now, tossing one fair die would give us S showing 1, 2, 3, 4, 5, and 6 as the total number of possibilities or total number of outcomes in that sample space. So when you toss one fair die, what are the possibilities? If you can envisage what possibilities to expect, then you can tell what should be in the sample space. So when you toss a fair die once, it is possible that a 1 may show up. It is also possible that a 2, a 3, a 4, a 5, or a 6 could show up. So if you put those outcomes together, they form a set S defining or describing the sample space for that fair die, okay? The tossing of that one fair die, okay? So now, so S equals 1, 2, 3, 4, 5, 6 are the possibilities you could have, the total number of possibilities you could have for tossing one fair die. So forming the sample space for one fair die is straightforward, is easy, and no complexity involved. Now let us consider the sample space for tossing two fair die. Now, it was easy to form the sample space for tossing one fair die, but it could become a little bit technical for forming this forming the sample space for tossing two fair dice. Okay, two fair dice. Now let's see. Now, when you want to form the sample space for tossing two fair dice, you must take into consideration or make certain assumptions. Rather, you must make certain assumptions, because those assumptions you make would help you. Now, the assumption we would make to start with is that the two die to be tossed, the two fair dice to be tossed, are uneven in their dimension, meaning that one can be considered a small die and the other one can be considered a big die. Why are we making this assumption? It is just to help us form a sample space with clarity. So the sample space for tossing a fair die can be presented, two fair dice can be presented in a table. Okay, now in this table, my assumption will be taken into consideration. What assumption is that? I'm going to create a table that shows one column carrying one particular column carrying 1, 2, 3, 4, 5, 6. Okay, 6 options, and the other particular column carrying 6 options also. Okay, so what would go in here? I'm going to write here in this particular place, this portion, I'm going to write here small die. Okay, and I'm going to write here big die. Okay, so this portion, by our assumption, would go for the small die. So one die will be assumed to be small and the other will be assumed to be big. Now, the essence of assuming that one die is small and the other is big is just for clarity, nothing else but clarity, to make you see vividly what is going on. Now, when you toss the small die and the big die at once, by assumption, the small die would have small inscriptions of 1, 2, 3, 4, 5, and 6, while the big die, by assumption, would have bigger inscriptions 1, 2, 3, 4, 5, and 6. Okay, now the possibilities are therefore these. It is possible that when you throw the first when you throw the two dice once, it is possible that the first die could land, the big die could land, showing you a big inscription 1, while the second one, the small die, shows you a small 1 as its inscription. And this could happen with the big one showing you 1 and the small one showing you 2, the big one showing you 1 and the small one showing you 3, the big one showing you 1 and the small one showing you 4, the big one showing you 1 and the small one showing you 5, the big one showing you 1 and the small one showing you 6. It is also possible that the big one could show you a big 2 and the small one will show you a small 1. The big die could show you a big 2 and the small die could show you a small 2. And this could continue to give us 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3, 7, or 4, 1 rather, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. For this option, you could have 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, and you could have lastly 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Now, take note of the fact that there are a total of 36 possible outcomes when two fair dice are tossed once. There are a total of 36 possible outcomes. So, what can we see or what can we deduce? Just like we did earlier on for a fair coin, a number of fair coins, it is possible to also see that the cardinality of the sample space the cardinality of the sample space generated when a number of fair dice are tossed once. The cardinality can be expressed as 2 raised to power x. In this case, x would no longer stand for the number of coins, but it will stand for the number of die. Okay? The number of dice. So, when x, clearly, when x is 1, ns will be 2, this will be 6, not 2. We are no longer talking about a coin. Now, take note, the 6 here stands for the number of sides a die has. And for this case, the 2 stood for the number of coins, number of sides a coin has. So, if we represent x, we use x to represent the number of dice, then ns, the cardinality of the sample space for tossing a number of fair dice, will be 6 raised to power x. In this case, when x is 1, ns, the number of elements or the number of outcomes in the sample space for tossing one die, will be 6 raised to power 1. It will be 6 raised to power 1, and that will give you 6. Now, when x is 2, ns, like we have just obtained, will be 6 raised to power 2, and that will be 36. Okay, so presenting the sample space for the tossing of 2 fair dice is better presented in a tabular manner, but presenting it for 1 fair die is just done using S equals this. Okay, so we could write or call this table S. So this table S represents the sample space for tossing 2 fair dice once. Now, by deduction, you could now see that when x is 3, ns for the tossing of 3 fair dice will be 6 raised to power 3, and that will give you 6 times 6 times 6. Okay, that will give you 6 times 6 times 6. So what is 6 times 6 times 6? That will be 36 times 6, giving you 6, 3, that is 18, and then that will give you 21, of course. So that will be 216. Okay, so that will be 216. Now, so there are 216 possibilities in the sample space for tossing 3 fair dice once, and you can go on and on and on to get the sample spaces for more than 3 fair dice tossed once. Now, is it possible to combine sample spaces? Is it possible to combine the sample spaces of 2 different random experiments? The answer is yes. Let us look at how we could combine the sample space for the tossing of 1 coin and probably one die. Okay, so let's see. Tossing 1 fair coin and 1 fair die. So let's see the sample space that will emerge. Now, for you to form this sample space, take note of this consideration. We are going to form a table that carries the colon depicting, the colon in this case will depict, so the column will depict the outcomes, the possible outcomes you could have for tossing the fair coin, while the row here will depict the 6 possibilities you could have for tossing the fair die. Okay, so I'm going to put here coin and I'm going to put here die. So for this row, I'm going to put 1, 2, 3, 4, 5, 6. So there are 6 possibilities when you toss a fair die, but there are 2 possibilities when you toss a fair coin. So let's combine them and see. So what will be the possibilities? What will be the sample space S for tossing 1 fair coin and 1 fair die once? That is throwing this and this at once. So if this is a die, this is my die. What will be the possibility? What will be the possibilities, or what will be the sample space for tossing this and this at once? What will be the sample space? Now, the consideration is that you could toss both of them and the coin would land showing you a head, when this other one, the die, shows you a 1. It could show you a head the coin and the other shows you a 2. It could have head 3 as a possibility. It could have head 4 as a possibility, head 5 as another possibility, and head 6 as a possibility. It could also be that a tail shows up first for the coin and a 1 shows up second for the die. It could be that you have tail 2, you could have tail 3, you could have tail 4, you could have tail 5, and you could have tail 6. So these are the possibilities you could have when a fair coin and one fair die are tossed once. So there are 12 possibilities, okay? There are 12 possibilities. So if you choose to write it in this manner, then you could write it as head 1, head 2, head 3, head 4, head 5, and head 6, okay? You could also write tail 1, or you just remove the comma. You could have tail 2, tail 3, tail 4, tail 5, and then finally tail 6. So these are the 12 possibilities you could have when you toss a fair coin and a fair die once. Now, what about tossing one fair coin or 2 fair coins and 1 die? 2 fair coins and a die. Let's see what are we going to have if that is the case. So for a random experiment involving 2 fair coins and 1 die tossed once, that is 2 fair coins and 1 die tossed once, what will be the sample space? So the sample space in this case could be presented first in tabular manner or could be presented just in tabular manner, and you will be okay. Okay, so this is my S. Now I'm going to put for the 2 fair coins. Take note, when the 2 fair coins are thrown, there are 4 possibilities for the coins. Okay, so if you remember, when we tossed 2 fair coins once, we had 4 possibilities: head, 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 tail, tail, head, and tail, tail. So those were the 4 possibilities. Now, in this case, in the case of tossing 2 fair coins once and 1 die also, you would have coin here and you have die. So for the die, you have possibilities 1, 2, 3, 4, 5, and 6. For the fair coin, you for the 2 fair coins, you have possibilities head, head, possibilities head, tail, possibility tail, head, and possibility tail, tail. So when you combine, head, head will combine with 1, head, head will combine with 2, head, head 3, head, head 4, head, head 5, and head, head 6. These are possibilities. You could also have head, tail 1, head, tail 2, head, tail 3, head, tail 4, head, tail 5, and head, tail 6. You could have tail, head 1, tail, head 2, tail, head 3, tail, head 4, tail, head 5, and tail, head 6. You could have tail, tail 1, tail, tail 2, tail, tail 3, tail, tail 4, tail, tail 5, and tail, tail 6. So these are possibilities. Now, I'm going to give you a task of, so that being the case, this is the sample space for tossing 2 fair coins and 1 die once. You could also form the sample space for tossing 1 fair coin and 2 fair dice. Okay, so you do that in your spare time. Form the sample space for tossing 1 fair coin and 2 fair dice once. You do that. Okay, so that being said, what have we said so far? For sample spaces, the sample space of a random experiment is the set of all possible outcomes for the random experiment. Okay, and we have in this video formed the sample spaces for 1 fair dice, 1 fair coin, 2 fair coins, 3 fair coins, 4 fair coins, 2 fair dice, and we've also shown you that you could combine the sample spaces of a fair coin and a fair die, 2 fair coins, and one fair die. Okay, so I'm giving you the task of obtaining the sample space for tossing 2 fair dice and 1 coin once. So you do that in your spare time. Now, corresponding to every sample space is what we call an event space. So we have just finished discussing the sample space of a random experiment or for a random experiment. Now, corresponding to every sample space is what is called an event space. What is an event space? Okay, what is an event space? Now, an event space is a subset, an event space for a random experiment is simply a subset of the sample space for that random experiment. So what is called an event space for a random experiment is simply a subset of the sample space for that random experiment. Now, event spaces are denoted with the letter E. That is uppercase E. We use uppercase E to represent event spaces. Now, I'm going to show you quickly how to obtain event spaces. But before doing that, let me start with showing you what the probability of an event is. Let's start with defining what the probability of an event is in terms of set theoretic definition. So, using set theoretic perspective, the probability of an event or an event space is defined as a ratio of the cardinality, of the event space to the sample space. Okay? So, when you take the ratio of the cardinality of the sample space to that of the ratio of the cardinality of the event space to that of the sample space, then you just will be defining the set theoretic definition of probability. So the set theoretic definition of probability requires that you take the ratio of the cardinality of the event space to that of the sample space. By this, we now mean that probability of E is given as NE, the cardinality of the event space, all over NS. So this is what we call the set theoretic definition of the probability of an event. Okay? So this describes, this here is the set theoretic definition of the probability of an event. So, what is the set theoretic definition of the probability of an event? It is the ratio of the cardinality of the event or event space to the cardinality of the sample space. So, using set theoretic perspective, the probability of an event or an event space is defined as a ratio of the cardinality of the event space to that of the sample space, and that can be expressed as PRE equals NE all over NS. Now, that being said, let us see what we discussed on event spaces. An event space for a random experiment is simply a subset of the sample space for that random experiment. Now, E, capital E or uppercase E, represents the event space conventionally. So now let us see how we could form several event spaces. So let's take an example. Number 1. Okay, so I'm going to use this example to show you how to solve problems using set theoretic definition, and I'm going to use this same example to show you how to form event spaces. Okay, so obtain the probability of having a head in the tossing of one fair coin. Okay, so a solution to this problem requires that we form the sample space first. So obtain the probability of having a head in the tossing of one fair coin. So what would that probability be? The first thing you have to do is to form the sample space. Now, what is the sample space for tossing one fair coin? It is head, tail. Okay? Now, what we define as the event space is a subset of the sample space, and in particular, it is a subset of interest. In this case, if you must obtain the probability of having a head, you must form an event space for a head. So let E be the event space. Let E be the event space for a head. Then E will be the set containing just head, meaning that E will be a singleton. Remember, a singleton is a set containing just one element. Now, by definition, probability of E, that's the probability of having a head, will now be NE all over NS. Now, what is NS? What is NE to start with? NE is 1. Why is NE 1? NE is 1 because in the event space, we only have one element, one outcome, which is just head. So NE, the cardinality of E, the number of outcomes in E will be 1. Now, what is NS? NS in this case will be 2 because in the sample space for tossing this one fair coin, we have two possibilities, head and tail. So the sample space will be 2. Therefore, the probability of having a head will be NE all over NS, which is 1 over 2. Now, if I choose to form another sample space containing a tail, you would notice that I could form another sample space. I could form another event space. So if I'm forming another event space for this question, I will quickly call this one, the first event space I formed, I will call it automatically E1. So E1 becomes the first event space I have formed in this question. So I'm changing everything to E1. Okay? So the probability of E1 will now be the probability of obtaining a head. Okay? In the tossing of one fair coin. Now, if I'm to find the probability of obtaining a tail in the tossing of one fair coin, I'm going to form another event space and I'm calling that one E2. Now, E2, let E2 be the event space. Let E2 be the event space for a tail. Then, E2 will be equal to T. It will also contain one outcome. Now, probability of E2 will be NE2 all over NS. What is NE2? NE2 will be the cardinality of this event space E2, and it contains just one event, that is tail. And this will be 2 also, giving you 1 over 2 as the probability. So, using SET theoretic definition, the probability of obtaining a head in the tossing of one fair coin is 1 over 2, and the probability of obtaining a tail in the tossing of one fair coin is also 1 over 2. Okay? And before we continue to another example, I'm going to use this example also, apart from using the example to show you how to solve a problem on SET theoretic definition, and also showing you how to form event spaces. Take note of one thing. I could also show you something called equi-probable sample spaces. Okay? Now, notice something about this particular sample space. Notice something about this particular sample space S that contains head and tail. Now, a sample space in which you have outcomes having equal probability of showing up is called an equi-probable sample space. Okay? So, a sample space that has the possibility of its outcome having equal probability is called an equi-probable sample space. So, I'm going to write here that an equi-probable An equiprobable sample space is a sample space in which individual outcomes have equal probabilities. Okay? So examples of equiprobable sample spaces are S equals head tail for tossing one fair coin once. S equals head tail, tail head, tail tail for tossing two fair coins once is an example of an equiprobable sample space. S equals 1, 2, 3, 4, 5, 6 is an equiprobable sample space, and so on. So you check this out. Why is this an equiprobable sample space? The probability of a head being an individual outcome in this sample space is 1/2 by our definition. Likewise, the probability of a tail is 1/2. In this sample space, the probability of having two heads showing up will be 1/4. The probability of having a first an outcome having the first head and the second tail is 1/4. So this individual outcome also has a probability of 1/4. The probability of having the first showing you tail and the second showing you head is 1/4. And the probability of two tails is 1/4. So in this second sample space, individual outcomes have equal probabilities of showing up. And that means that this sample space is an equiprobable sample space. In this particular sample space, for tossing one fair die once, 1/6, 1/6, 1/6, 1/6, 1/6, 1/6 are the probabilities, respective probabilities of a 1, a 2, a 3, a 4, a 5, a 6 showing up as individual outcomes in this sample space. So what do we call an equiprobable sample space? An equiprobable sample space is a sample space in which individual outcomes have equal probabilities. Okay? Now, the probabilities of each outcome in the sample space for tossing two fair dice once is also an equiprobable sample space, because each outcome in the sample space has equal probabilities of showing up. Okay? So you check that out. Now let's go to example 2. But before we go to example 2, let me also tell you something about an equiprobable sample space. Now, aside the fact that an equiprobable sample space is a sample space in which individual outcomes have equal probabilities, there is something also called each of these events or each of these outcomes are called equiprobable outcomes because they have equal probabilities of showing up. So in an equiprobable sample space, you have equiprobable outcomes. The outcomes are called equiprobable simply because they all have equal probabilities of showing up. So equiprobable outcomes are individual outcomes in a sample space having equal chance or chances of showing up or occurring. Okay, so that is what I'm going to say here. Now let's take an example, example number 2. Let's take another example number 2. Now, what if we are given a question like this? What is the probability of having a head and tail showing up? What's the probability of having a head and tail showing up in the tossing of two fair coins once. So what is the probability of having a head and a tail showing up in the tossing of two fair coins once? Now, as a solution to the problem, the first thing, of course, we shall do will be to form the sample space. The sample space for what kind of experiment? The experiment of tossing two fair coins once. So that will contain head, 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 tail, tail, head, and tail, tail. Now, take note of one thing about this question. This question did not demand the probability of a head showing up first and a tail showing up second. That would be a different question. The probability required is the probability of having a head and a tail. So it is not specific. The question is not specific about which should show up. And that means we are going to form an event space, E. So let E be the event space for a head and a tail showing up. Now, if E is the event space for a head and a tail showing up, then E would contain head, tail, and tail, head as the possibilities. Now, why is that so? The question was not specific about which one should show up first and which should show up second. So, in this event space, we are going to accommodate head, tail, and tail, head as the possibilities of having head and tail. Now, what is the cardinality of E? The cardinality is 2. What is the cardinality of S? It is 4. And that means the probability of E being the probability of a head and a tail showing up will be NE all over NS, and that will give us 2 over 4, which is 1 over 2. Now, if you were to obtain the probability of having two tails showing up, you could form another event space. Let E2, so we are going to call this one E1 in that case. If we were required to find the probability of two tails showing up, we are going to form another event space, E2, and automatically the first event space we form becomes E1. So let E2 be the event space for two tails. In this case, the probability of E2 clearly will be NE2 all over NS, and that will be what? That will be 1 over 4. Why is it 1 over 4? In the event space for E2, you are going to have just one outcome. That is, E2 as an event space will contain one outcome, tail, tail. Okay? So tail, tail, remember, is considered as an outcome because two coins are tossed once. So NE2 automatically will become 1 because there is just one outcome, tail, tail, in that event space. And the probability will be NE2, which is 1, all over NS, which is 4. Okay? So please, for more questions or for problem solving on probability theory, please check out our videos that we shall be uploading subsequently on the solver series on probability theory. The solver series on probability theory. In that particular video, we shall focus on solving a lot of problems on probability theory, especially as it concerns what we have done so far. Thank you very much for watching this video. Thank you for your time. We are very grateful from the decks of GER Hub. In our subsequent video, our next video, we shall be looking at showing you that the probability of an event must lie between 0 and 1, with 1 and 0 inclusive. And we shall be showing you other things. Thank you very much.